Hi everybody! So in today's video we're going to be working on solving differential equations. Now in order to solve a differential equation we're going to need to be really comfortable with the algebraic manipulations that we practiced and discussed today in class. Today we're really going to focus in this video on the calculus parts of this process. So let's start by defining what a differential equation is. A differential equation is an equation where we know the derivative of a function and we can use antiderivatives to find the functions. Now the directions are often going to say that we are trying to solve the differential equation. When the directions say that we are trying to solve the differential equation, what it really means is to figure out the original function based on the derivative that we have. So if we know the derivative, can we figure out the original? So I'm going to zoom in just a little bit because there is going to be a lot of detail today, which means I have to really watch the edges of my paper so it doesn't go off the screen. Now, for example, if it says in this problem that the derivative of my function is 3x squared, then the original function would have been x to the third power plus c. Now that's nothing new. We've done this before. What makes solving a differential equation different is that now we're going to need to figure out c. So once we've done this process, which we've kind of been familiar with before, it's just the antiderivative based on the derivative, we're going to now figure out the c value that's missing. And the way that we do that is using something called an initial value. So if we have an initial value, or in other words, an ordered pair that we know was part of the original function, we can calculate the c. Now we did this several times in class today. Basically, the antiderivative part is really the new part that we haven't practiced yet. So when we have an initial value and we use it to calculate the c, we call this finding the particular solution. So for example, if I told you in addition to knowing the derivative was 3x squared, we also knew that the original function crossed through the point 2, 14, then what we would be able to do is say, well, if the derivative is 3x squared, then the original would be x cubed plus c. And then we would be able to take this x and y value and substitute them into this equation. So we would have 14 equals, and instead of x we would have 2 cubed plus c. And then this just becomes an equation that we can solve. So we have 14 equals 8 plus c, which means c would have to be 6. If we then use that number and we plug it back into our original antiderivative that we set up instead of the c value, we would know that our solution to this differential equation was x cubed plus 6. Now this right here is called the particular solution. And the reason we call this the particular solution is because we solved this equation for a particular or specific value of c. We would call this the general solution. And the reason we would call this the general solution is that in general, all of the solutions to this differential equation are going to have this format. It's going to be x cubed plus some constant, but what constant we put there depends on the initial value. So this is the general template, and this is the particular solution that crosses through the correct ordered pair that we were looking for. Now throughout this process, we're going to be looking at questions that have a variety of complications that result from algebraic manipulations. So it's good to have a process that we can use to solve these kinds of problems that we can think through each time and make sure that we're following these steps so we can get the correct original function. So the first step is always going to be to separate the variables. A lot of the problems that we are going to do are going to have an x and a y in the problem. Many of the equations will have an x and a y in the equation. When you see that the derivative is defined in terms of x and y, we're going to need to separate all the y's to the left side of the equal sign and all the x's to the right side before we can solve the problem. Then, because we're going to be trying to find the original function using the derivative, we're going to use an integral to find the antiderivative on both sides of the equation. We're going to write a plus c on one side only. And the reason we're going to write the plus c on one side only is that it's not really necessary to have a constant on both sides, since when we solved and got y by itself, it would condense the constants to one side always. Then we're going to solve for c, if possible. We want to use our initial value to find c whenever we can. And then lastly, we're going to rearrange the problem and solve to get y by itself. At the end of the day, we want to have the equation of the original. And typically that means we're going to want to write that equation where y is by itself. So let's go ahead and work through some of these problems. We're going to start with problems that don't have a mixture of variables. All of these problems are going to be in terms of just x. So here's what I mean by that. If I look at the equation in problem number 1, I can see that the derivative is equal to secant squared of x plus 2x plus 5. On the side of the equation over here, on the right side, all of these terms are just in terms of x. Now on the next page of our notes, I'm just going to give you a quick preview. We're going to be looking at equations that are in terms of x and y. In other words, the right side of the equal sign has both an x and a y in it. So as a result, we're going to need to be really careful there to separate our variables. Now on this page, the first step would be to separate the variables, but since the right side of the equal sign is only in terms of x, that doesn't require us to really do very much work. All we would really have to do is multiply by dx on both sides, so that the left side of the equation is just going to have the dy, and the right side of the equation is going to have the secant squared of x plus 2x plus 5 all times dx. Now our next step is going to be to use an integral on both sides. And the reason we're going to use an integral is that we know that doing the integral of a function helps us figure out the antiderivative. We go backwards, we figure out the original. Now the invisible number here by the dy would be a 1. So the antiderivative of just the number 1 would just be y. On the right side of the equation, the antiderivative of secant squared would be tangent of x. The antiderivative of 2x would be x squared. And the antiderivative of 5 would be 5x. And then, of course, I need to put a plus c on one side only. Usually, we choose to write the plus c on the right-hand side. Now, for this specific problem, we're done when we get to this point. The reason we're finished is that there is no initial value, so I can't go any further and actually figure out what the c value would be. In other words, in this problem, the best we can do is figure out the general solution. Now let's go ahead and look at an example where we have an initial value and see how that changes our process a little bit. In problem number 2, we have an ordered pair as part of the question that we know the original graph passed through. What that means is that we're going to be able to pin down the exact value of c that we were looking for. Now in order to do that, we're still going to do step 1, which is to separate the variables. So we're going to multiply by dx on both sides. That way the left side of the equal sign just has y, and the right side of the equal sign just has x. Now we're going to use an integral, and therefore an antiderivative, to figure out what the original function would have looked like. The invisible number here by the dy is just a 1, so the antiderivative would just be y. And the antiderivative of e to the x is e to the x. The antiderivative of 6x squared is minus 2x cubed. And then I'm going to put my plus c Again, I'm only writing the plus c on the right-hand side. Now, in the previous problem, that was as far as we could go. We didn't have an initial value. We couldn't figure out our c and pin it down exactly. But in this problem, what I'm going to do is take the ordered pair and I'm going to plug it into this equation. Now, I like to draw a line here to separate that this is sort of a detour. We're going to write the final answer when we're done with this step. So I'm going to plug in the y is a 0. I'm going to have e to the 1, because the x is a 1, minus 2 times 1 cubed plus c. Now if I solve this, I get 0 equals e minus 2 plus c, so c would equal 2 minus e. I'm going to add the 2 and subtract the e. Now after I'm done with that detour, my final step is going to be to take the c that I just calculated and substitute it back into the equation that I had before. So my final equation here would be y equals e to the x minus 2x cubed plus 2 minus e. The y is by itself. I've replaced the c with the c value that I calculated, and so I'm done. This equation is what we would call a particular solution, because we actually pinned down the exact value of c that we were looking for. Let's go ahead and look at the next problem. So the next problem is a little bit more complicated. We're lucky that it's still only got x's on the right-hand side of the equal sign, but we still need to get the x's all on one side and the y's on the other side. So we're going to multiply by dx on both sides. Now, what makes this problem slightly more complicated is that when I do the integral, in order to do the antiderivative, the left side of the equation is fairly straightforward. There's an invisible 1, so the antiderivative is just y. The right side of the equation is a little bit more complex. This is the type of problem where we would traditionally use a U-substitution. So in order to complete the process of integrating the right side, I'm going to do a U-substitution. My u here would be my tangent function, because that is what would have caused the chain rule. Now du dx would be secant squared of x, and if I solve for dx, I would have du divided by secant squared of x. Now I'm going to substitute that only on the right side. So I'm going to have the integral of the square root of u times secant squared of x, and then instead of the dx, I'm going to have times du over secant squared of x. Now I'm lucky in that the secant squareds are going to cancel, so my new problem becomes the integral of the square root of u du. Now I know that in order to undo a square root, I usually like to think about that as being u to the 1/2 power. So I would rewrite this as u to the 1/2 power du. Now the antiderivative of u to the 1/2 power would be u to the 3/2 power, and then I need to divide by 3/2, so I would have 2/3 u to the 3/2 power plus c. Now the one thing that makes this a little bit different than the last time we've done a u substitution is that we don't want u's in our final answer. Normally what we would do is we would change the bounds of the integral and just plug in those numbers. So everything would be in terms of u. But in this problem, it's not possible to change the bounds. We're not using an integral to calculate an area here. We're using an integral to force an antiderivative to get back to the original function. So what I need to do is I need to take this u and re-substitute it into this function so that my function has y's and x's again. So I would have 2/3, and instead of u, I would write tangent of x to the 3/2 power plus c. Since we don't have an ordered pair here, we can't figure out the particular solution, so we're going to leave this answer as the general solution. Now let's go ahead and look at some problems where the problems have a combination of x's and y's on the right-hand side of the equation. So in problem number 4, you'll notice that the right-hand side of the equation has a combination of x and y. This time, one of the more complicated steps is to separate your variables. In the previous problems, it was fairly easy to do this. We just needed to multiply by dx. Here, it's going to take a little bit more work. So we're going to go ahead and multiply by dx, just like we did before. And that's going to give me dy equals 3xy times dx. Then we're going to divide by y. So we're going to have 1 over y times dy equals 3x times dx. Now we're going to use an integral to get the antiderivative, to sort of force that to happen. The antiderivative of 1 over y would be the natural log of the absolute value of y. The antiderivative of 3x would be 3 over 2x squared plus c. Now we don't have an ordered pair here to plug in, so it's not possible for us to solve and figure out c, which means our last step is going to be to get the y by itself. You always want to write your final answer as y equals something. In order to make an ln go away, we use e because ln and e are inverse functions. So we have the absolute value of y equals e to the 3 over 2x squared plus c. Now, one of the things we've discussed is that when you have a plus sign in the exponent, that actually originated as a multiplication problem because of our exponent rules. And e to the c is just a constant. So we could rewrite this equation as the absolute value of y equals c times e to the 3 over 2x squared. Now the last step is to try to get that absolute value to go away. But since an absolute value problem always has two answers, in order to make the absolute value go away, we need to put plus or minus c times e to the 3 over 2x squared. And that would be your final answer. That's your general solution. The reason it's a general solution is we haven't pinned down an exact value of c. Now the last example we're going to do today is very similar to the one we just did, where there are x's and y's both combined into one equation, but we're just going to do this with an initial value this time. So now for number 5, we're going to separate the x's and y's, which means I'm going to multiply by dx on both sides, and I'm going to get dy equals x squared y squared times dx. And then I'm going to divide by y squared on both sides. So I'm going to get 1 over y squared times dy equals x squared times dx. Now I'm going to use an integral in order to force an antiderivative, sort of get rid of this derivative that we have. So the antiderivative of y squared I think is easier to calculate if you rewrite this as y to the negative 2 power. Then I would do the antiderivative on both sides, so I would have y to the negative 1 times negative 1 equals 1/3 x cubed plus c. Since this time we have an ordered pair, I'm going to go ahead and substitute that ordered pair into this equation and calculate my exact c value before I try to isolate y. So if I'm going to do this in blue, that way the isolation part happens in green. So I'm going to go ahead and substitute that in, and I get negative 1 times 1 to the negative 1 equals 1/3 times 1 cubed plus c. Now 1 to the negative 1 really means 1 divided by 1, so that would just be 1. So I have negative 1 equals 1/3 plus c, which means c would equal -1 minus 1/3, which is -4/3. Now that I have that exact value of c calculated, I'm going to plug it back into this function, and I'm going to go ahead and isolate y after that's plugged in. So I'm going to have -1 y to the -1 equals 1/3 x cubed, and instead of c, I'm going to write -4/3. Now I think instead of leaving the function like this, it's actually easier to isolate y if I rewrite this like this. -1 over y equals 1/3 x cubed minus 4/3. Now, using one of the algebra things we practiced today in class, what we know is that y would equal -1 over 1/3 x cubed minus 4/3. And if I want to make this look a little bit nicer, which oftentimes I do, I'm going to go ahead and multiply by 3 on both the top and the bottom so that I can get rid of this whole fraction inside of another fraction thing. So I would get -3 over, when I distribute the 3 to the denominator of the overall fraction, the 3 and the 1/3 cancel and I just get x cubed. The 3 and the 3 cancel and I just get -4, and I'm done. All right, I know there's a lot of algebra going on here. Hopefully it makes sense and you can see the connection between the types of algebra things we're going to be asking you to do here and the types of algebra things that we did today in class. Thank you so much for watching this video and have a great night. I will see you tomorrow for some practice.